For as long as human beings have looked up into the night sky, we have circled around the same impossible question. How did all of this begin? Every star burning in the darkness, every galaxy drifting across the cosmic web, every atom inside your body, all of it can be traced backward through time toward a single moment nearly 14 billion years ago. We call that moment the Big Bang. And while modern science has uncovered extraordinary details about it, the deeper we look, the stranger the story becomes. The Big Bang is often imagined incorrectly. People picture an explosion, matter erupting outward into an already empty universe. But according to modern cosmology, that is not what happened at all. The Big Bang was not an explosion inside space. It was the expansion of space itself. Every region of the universe expanded simultaneously, carrying matter and energy along with it. Even more unsettling, time itself may have begun in that same event. This idea emerges directly from Einstein's general theory of relativity, which revealed that space and time are not separate things but parts of a single structure, spacetime. When physicists mathematically reverse the expansion of the universe, spacetime contracts toward a boundary where density and temperature rise without limit, and the equations themselves collapse. This boundary is called a singularity, a point where our understanding of physics stops functioning. And that creates a disturbing possibility. If time itself originated in the Big Bang, then asking what happened before, it may not make sense. It could be like asking what lies north of the North Pole. The question feels meaningful because our brains are built around cause and sequence, but reality may not obey those intuitions at the deepest level. Still, science rarely accepts the first answer as the final one. We cannot observe the Big Bang directly, but the universe left behind evidence of its infancy, a relic that still surrounds us today. It is called the cosmic microwave background, or CMB, faint radiation filling all of space, released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that moment, the cosmos was an opaque plasma, a blinding fog so hot and dense that light itself could not move freely through it. But as expansion continued, temperatures dropped, atoms formed, and suddenly light was able to travel unimpeded for the first time. That ancient radiation has been crossing the universe ever since, stretched by billions of years of cosmic expansion into microwave wavelengths invisible to human eyes. In a very real sense, the CMB is the oldest image humanity will ever see. And hidden inside it are tiny temperature fluctuations, differences smaller than a fraction of a degree, representing the seeds from which every structure in the modern universe eventually emerged. Galaxies, galaxy clusters, and the vast filaments stretching across cosmic space all grew from these minute irregularities imprinted into the early universe. But studying this ancient light revealed something deeply unsettling. Everything we can directly observe, stars, planets, nebulae, galaxies, black holes, dust clouds, appears to make up only about 5% of the total universe. The remaining 95% is invisible. Roughly 27% seems to consist of dark matter. Without it, galaxies should never have formed as quickly as they did. The visible matter alone simply does not provide enough gravitational pull to explain the structures we see across the cosmos. And then there is dark energy. Accounting for roughly 68% of the universe, dark energy appears to be causing the expansion of space itself to accelerate. This discovery shocked astronomers in the late 1990s. By observing distant exploding stars known as supernovae, scientists realized the universe was not merely expanding, it was expanding faster over time. Something, somehow, was pushing galaxies apart. No one knows what that something is. Even more troubling, recent observations hint that dark energy may not be constant. If its strength changes over time, then the ultimate fate of the universe becomes uncertain. Endless expansion is only one possibility among several. As cosmologists pushed deeper into the universe's history, the story grew stranger still. After the cosmic microwave background was released, the universe entered a period known as the Cosmic Dark Ages. For hundreds of millions of years, there were no stars and no galaxies, only cooling hydrogen and helium drifting through darkness. Then gravity slowly transformed the cosmos. Gas clouds collapsed inward, temperatures rose, and eventually the first stars ignited. These early stars were nothing like our sun. They were colossal, unstable giants, burning with incredible intensity. Their lives were brief and their deaths violent. When they exploded as supernovae, they forged and scattered the first heavy elements: carbon, oxygen, iron, the raw ingredients that would later form planets, oceans, atmospheres, and life itself. The light from those first stars ended the cosmic dark ages forever. Today, humanity possesses a machine capable of looking back toward that era with unprecedented clarity. The James Webb Space Telescope. By observing extremely distant infrared light, Webb is allowing astronomers to witness some of the earliest galaxies ever formed. And what it is finding has become one of the biggest surprises in modern cosmology. Galaxies are appearing earlier, brighter, and more evolved than current models predicted. Some observations suggest that enormous galaxy-like structures already existed only 500 to 700 million years after the Big Bang. Systems so massive and mature that, according to standard theories of cosmic evolution, they should not have had enough time to form. Astronomers began calling them universe breakers. The nickname was only half joking. At the same time, another problem has been quietly growing in the background, one that cuts directly into the foundations of cosmology itself. It is known as the Hubble tension. The Hubble constant describes how fast the universe is expanding. But there are two ways to calculate it, and the answers refuse to agree. Measurements based on the early universe, particularly the cosmic microwave background, predict one value. Measurements based on nearby galaxies and supernovae consistently produce a larger one. The discrepancy is not tiny. It is persistent, statistically significant, and has survived years of attempts to explain it away. Something in our understanding of the cosmos appears incomplete. Possibly the early universe, possibly the modern universe, possibly both. These tensions have led some physicists to ask a radical question. What if the Big Bang was not truly the beginning of everything? One idea comes from quantum gravity cosmology. In this framework, the singularity never actually forms because quantum effects prevent matter from compressing into infinite density. Instead, the universe contracts to a minimum size and then rebounds outward in a colossal expansion, a big bounce. In this model, our universe could be the latest phase in an eternal cycle of collapse and rebirth. Another, even more controversial idea was proposed by Roger Penrose through a theory called conformal cyclic cosmology. Penrose suggests that the universe passes through infinite cosmic cycles called aeons. At the end of each cycle, all matter eventually decays away, leaving only radiation in an unimaginably cold and empty cosmos. Without matter, concepts like distance and time scale lose physical meaning. Penrose argues that such a universe becomes mathematically equivalent to the conditions of a new Big Bang. In other words, the end of one universe may become the beginning of the next. Even more remarkably, Penrose believes traces of previous cosmic cycles may already exist within the cosmic microwave background itself. His team identified unusual circular patterns, subtle rings in the temperature data detected independently by both the WMAP and Planck space missions. He refers to these anomalies as Hawking points, possible remnants of evaporating supermassive black holes from a universe that existed before ours. Many physicists remain unconvinced. Critics argue the patterns are likely statistical noise rather than evidence of a previous cosmos. But history has a habit of turning impossible ideas into accepted science. Black holes themselves were once dismissed as mathematical absurdities. Today we photograph them directly, and beneath all of these theories lies an even deeper problem: the meaning of nothing itself. Modern quantum physics suggests that empty space is not truly empty. Even a vacuum seethes with activity. Quantum fields fluctuate constantly. Particles briefly appear and vanish, Energy rises and falls spontaneously on microscopic scales. Through nothingness, a complete absence of space, time, matter, energy, and physical law may not exist at all. Perhaps the universe emerged from a quantum fluctuation beyond the limits of our space-time. Perhaps it rebounded from a previous cosmic phase. Perhaps time itself is part of a larger structure our current mathematics cannot yet describe. What makes this story so extraordinary is that the Big Bang theory itself remains one of the most successful scientific frameworks ever developed. It explains the expansion of the universe, the existence of the cosmic microwave background, the abundance of light elements created in the first minutes after the Big Bang, and the large-scale structure of the cosmos with astonishing accuracy. Its foundations are not collapsing. But the deeper we investigate the earliest moments of existence, the more reality resists simple explanation. The James Webb Space Telescope is revealing galaxies that challenge our timelines. Precision measurements are exposing contradictions in our understanding of cosmic expansion. Theories once considered speculative are being revisited seriously because the universe itself keeps presenting mysteries our current models struggle to explain. And perhaps that is the most important lesson of all. Science has not solved the mystery of the universe's beginning. It has revealed something even more profound. Reality is stranger, deeper, and more subtle than human intuition ever expected. Every time we build a more powerful telescope, every time we push mathematics a little further, every time we measure the cosmos with greater precision, the universe opens another door we did not know existed. The ultimate question may not be how the universe began. It may be whether the word beginning is even the right way to describe what happened at all.